Hello, this is Pat Hindle, editor at Microwave Journal. It is my pleasure to welcome you all to this session in our technical webinar series on VCO Fundamentals. Before we start, there are a few items that I'd like to bring to the attention of our viewers. Today's presentation is approximately 45 minutes long, after which time we'll hold a question and answer session with our presenter. You may submit a question through the website at any time during the presentation through the Q&A box. We'll wait to the end of the presentation to go through the Q&A. Please address your questions to all presenters, which is the default setting in the Q&A box. This presentation will be archived and available for viewing later on in the events section of the Microwave Journal website. Also, if you'd like to see more details, simply click on the Enlarge button. Our sponsor today is Mini Circuits. They provide RF, IF, and microwave products from DC to 40 gigahertz. While Mini Circuits is headquartered in Brooklyn, New York, they have design centers around the world. Their core technologies include core and wire, microstrip, LPCC, and semiconductors. They have more than 10,000 active products with more than 20,000 customers. They meet the highest quality and environmental standards to deliver high-performance products to their customers. Mini Circuits has a very broad product offering. They have approximately 28 product lines covering almost every type of active and passive device. These include VCOs covered here today. Mini Circuits has more than 800 catalog VCOs from 12 megahertz to 6.8 gigahertz, with hundreds more ready for fast turnaround. All are available for rapid customization, covering from 3 megahertz to 7.1 gigahertz. They have a wide variety of frequency ranges, performance specifications, and packaging types. At Mini Circuits, you could search through millions of live test data points from thousands of products to meet or exceed your performance requirements. The search engine includes standard and custom products, including those under development. A wide variety of component types are included to meet all your needs. Visit minicircuits.com to find out more. Today's speaker is Dr. John McNeil. Dr. McNeil received his bachelor's degree from Dartmouth College and master's degree from University of Rochester and PhD from Boston University. From 1983 to 1990, he worked in the industry in the design of high-speed, high-resolution analog-to-digital converters and low-noise interface electronics used in high-speed, wide dynamic range imaging systems. Since 1994, he has been with the Electrical and Computer Engineering Department of Worcester Polytechnic Institute, where in 1999 he received WPI's campus-wide award for outstanding teaching. His research interests are in the area of analog and mixed-signal integrated circuit design for phase-lock loop, analog-to-digital converter, and instrumentation applications. At this point, I'll turn the presentation over to John.
Here's an overview of what we'll be talking about today. First of all, good morning, good afternoon, or good evening to everyone, wherever you are. Thanks for taking the time to take part in this webinar today. As Pat said, there will be time for questions. Feel free to send them in during the presentation, and we'll address them afterward. An overview of what we'll be looking at. First, just the functional block concept of what a voltage-controlled oscillator is. We'll review some oscillator fundamentals and basic performance metrics. We'll look at methods of tuning and how those affect the performance metrics for VCOs. We'll finish with some advanced performance metrics prior to concluding. So first, applications and specifications for the basic VCO functional block. The VCO concept is shown here. The output of the voltage-controlled oscillator is a sinusoid in the time domain, an impulse in the frequency domain, ideally. And the concept is the frequency of oscillation is a function of the tuning voltage applied to the input of the VCO. Ideally would be a linear function, but as long as we have some control of the oscillation frequency with that tuning voltage at the input, that's what the VCO is intended to do. Some typical applications in an RF system, typically we're trying to tune among many RF channels. Shown here is one channel, but we could be looking for information in an adjacent channel or another adjacent channel. By tuning a local oscillator to different frequencies, we can then tune one of these channels down to an IF or to baseband. So channel selection, tuning the local oscillator to different frequencies is one of the functions. And a phase lock loop system will typically use a VCO embedded in the phase lock loop to down-convert the band of interest to IF. So the VCO enables electrically tunable selection in an RF system. In a digital system, frequently we want to use an on-chip clock for a processor at a higher multiple of an off-chip clock frequency. So in this case, the output of the VCO is a particular clock frequency. The output of the VCO is fed back through a divider. Let's look at an example of a divide by 2 digital divider. So this divided frequency is equal to F out over 2. The VCO or the phase lock loop rather, is a negative feedback loop that will drive the 2 input frequencies at the input of the phase detector to be equal. So our input frequency is equal to F out over 2 once the loop has locked. So F out is then equal to a multiple of F in this case 2 times F in. And depending on the divider ratio implemented in the feedback, we can achieve synthesis of higher frequency clocks locked to the input clock frequency. The specifications that you see for VCOs shown here in a snapshot from the Mini Circuits web page. Many different frequencies, different types of specifications. We'll be covering these in today's presentation. So let's move on to a review of oscillator fundamentals, controlling frequency and amplitude, and different types of oscillators that can be used as VCOs. The first we'll look at is multivibrator, followed by ring, resonant, and feedback oscillators. And for each of these designs, we'll look at what determines frequency, what determines the amplitude and output power, and how things start up. So the first we'll look at is a multivibrator. A conceptual multivibrator oscillator is shown here. It's characterized by having only one energy storage element, typically a capacitor. It's also referred to as an astable or a relaxation oscillator. Here's a slightly more detailed general example of the multivibrator oscillator. We've got some kind of nonlinear control block, typically a Schmidt trigger, with 2 thresholds plus or minus Vref. We'll imagine that the capacitor begins in a grounded state with the switch to the discharging current Iref. The capacitor voltage will ramp towards one of the thresholds. In this case, ramping down, it'll hit negative Vref. The state of the Schmidt trigger will change, and the capacitor will ramp up towards positive Vref. Hitting positive Vref, the Schmidt trigger will turn it around and head down. And we complete one cycle. The timing of the cycle is controlled by the charging current Iref, the value of the capacitance, and the Vref thresholds. These also control the amplitude, the thresholds of the logic swing. Startup is guaranteed for a multivibrator. There's no stable state. It will continuously oscillate between the 2 extremes. A digitally friendly VCO architecture is the ring oscillator. We have N stages, typically an odd number, so we have a phase inversion around the ring. And following one edge around the ring, the rising edge of A will cause a falling edge of B, 1 propagation delay later. falling edge of B, rising edge of C. The edge propagates around the ring, and a complete cycle will occur in 2n propagation delays. So the oscillation frequency for the ring oscillator, 1 over 2n times the propagation delay. So in this case, the frequency is controlled by the gate delay of the logic converter. Amplitude is controlled by the logic swing. And like the multivibrator, startup is guaranteed. There is no stable state. For higher performance applications, a resonant oscillator can be used. The concept here is the natural oscillation frequency of a resonance where energy flows back and forth between two energy storage modes, typically the magnetic field in an inductor and the electric field in a capacitance. The oscillation frequency is determined by the resonance, 1 over 2 pi square root LC. And to consider some of the concepts for the resonant oscillator, we'll use a mechanical analogy, shown here a playground swing set. If we imagine someone sitting on the swing, and we'll keep track of the state of this system by the angle that the swing makes with the vertical. And we'll start with an ideal case, assuming no losses. In the mechanical analogy, the two energy storage modes are potential and kinetic energy. And if we imagine giving this system an initial condition, a displacement with zero velocity, all the energy of the system is in potential energy. So I have maximum potential energy here in my initial condition. We'll let the swing go. It'll swing down through zero angle where it reaches maximum velocity, and that's where I have maximum kinetic energy. And the system will just keep oscillating between maximum and minimum kinetic energy and potential energy. The energy is traded back and forth between potential and kinetic energy. And ideally, this energy just stays forever trading back and forth between these two modes. The frequency is controlled by the length of the pendulum and also the gravitational constant G. The amplitude is controlled by the initial position. And to start up this oscillator, we do need some initial conditions, some energy input. For the real resonant oscillator, there are going to be losses. We're going to have friction, wind resistance. So with every cycle, a little more energy is lost, and we'll see the amplitude decreasing with time. So any loss term in the electrical version of the oscillator is going to be any resistive loss terms. It turns the organized energy of potential and kinetic energy into disorganized thermal energy. The amplitude will decay towards zero. So we require some kind of energy input to maintain amplitude. In the mechanical case, that's the person on the swing pumping their feet back and forth to feed energy back into the system at the right frequency. And we need to do that electrically somehow for the LC oscillator. Similarly, for the LC resonant oscillator, ideally the energy is traded back and forth between the electric field and the capacitor, the magnetic field and the inductor. With no losses, an initial energy input would give us oscillation at constant amplitude forever. In reality, we don't see that. Modeling losses in the system as this series resistance, we will see a mechanism for converting the magnetic or electric field energy into thermal energy, and we see the amplitude decaying to zero. So eventually the oscillation would just die out. The Q of the resonator tells us how many cycles we would get until the oscillation would die out. It's a measure of the quality of the resonance and tells us how much energy we need to feed back in to maintain oscillation. So the problem is the loss of energy due to non-ideal inductors and capacitors. one way we can put in the energy required to maintain the amplitude is synthesis of a negative resistance, and negative resistance in parallel with the positive loss resistance will cancel out the losses. The negative resistance will feed energy back in to compensate for the energy lost in the resonance. So one way to synthesize a negative resistance is shown here with an op-amp. You can do it with other amplifiers as well. Looking at the resistance at this node, we'll apply a test voltage and see what current flows and calculate Vx over Ix as the input resistance. Well, Vx is the voltage here. If I have equal value resistors for the op-amp, I'll get 2 Vx at the output. The voltage drop on this resistor R in the feedback is equal to Vx, but plus to minus this way, giving me a current Vx over R flowing out of this node. So the equivalent resistance looking in is minus R. So the amplifier, in this case, with the positive feedback, will allow us to feed energy into the resonator to counteract the losses in R loss. Another type of oscillator, the feedback oscillator, is shown here, the Wien bridge oscillator. Typically, the Wien bridge is used at audio frequencies rather than the RF frequencies we're going to be featuring later on. But I think the principles of the feedback oscillator are useful in understanding oscillator performance. So on the left is shown the schematic of the Wien bridge oscillator as it's typically seen. We'll redraw it in a form to show the feedback nature of the circuit. We've got an amplifier with a forward gain A, which is just given by R1 plus R2 over R1. And then that's fed back around the loop through this beta network with resistors and capacitors. The transfer function of the beta network is shown below. At the resonant frequency, at the oscillation frequency where we intend to operate, the beta feedback network has a magnitude gain of 1/3 and a phase shift of 0. So we'll do a thought experiment where we break this loop, inject a sine wave at point P, and see what comes back around the loop. So imagine a switch connecting this sine wave source to Vx, and we'll apply a 1-volt source sine wave at our oscillation frequency, F oscillation. So here's Vx with a 1-volt amplitude. If I set the R1 and R2 values to give a gain of 3 from input to output, then the output of the op-amp will be a 3-volt sine wave. Feeding back through the transfer function of the beta network, what I'll see at point P is in phase, but attenuated by the 1/3 factor. So I'll have a 1-volt sine wave in phase feeding back at point P. So if I have the gain and the phase of the loop just right around this feedback, a 1-volt sine wave at Vx results in a 1-volt sine wave at point P. If I imagine flipping this switch, I've got a self-sustaining waveform, and the loop will just continue oscillating with a 1-volt amplitude. But what happens if I'm not just right? If I imagine putting in my 1-volt sine wave and the gain around the loop is a little bit less, say 0.99, 1 volt becomes 2.97 volts at the output of the op-amp, becomes 0.99 volts, there's not enough waveform being transmitted around the loop to sustain oscillation. The next cycle, 0.99 becomes 0.98, and the waveform will decay away and die out. On the other hand, if I'm a little too aggressive with my gain and have a gain of 1 around the loop, my 1 volt sine wave will turn into something a little greater than 3 volts at the output of the op amp, giving me something a little too big at point P. So when I flip the switch over, 1 volt becomes 1.01, 1.02, and the waveform will grow exponentially. So the feedback oscillator, to maintain stable oscillation, requires exactly unity gain around the loop. So what we'll have is some kind of supervisory circuit that monitors the amplitude of the output and then controls some parameter in the loop, typically the gain of the amplifier. And if the supervisory circuit sees the amplitude either exceeding or decaying away from the target amplitude, it will change the gain to maintain exact unity gain around the loop. So we need some supervisory circuit to monitor the amplitude. This circuit can start up with random noise as long as the supervisory circuit begins with loop gain greater than 1. So how this affects the real resonant oscillator, we need to balance the losses with the correct value of the negative resistance. If R neg is just right, we will have a sustained oscillation. If R neg is a little bit too small, the amplitude will decay away. If R neg is too big in magnitude, then we're feeding too much energy into the resonator and the amplitude will increase. The frequency is determined by the LC network. Startup will again come from random noise as long as we begin with the negative resistor large enough to overcome the maximum loss. As the amplitude grows, typically a soft clipping in the negative resistance mechanism can give us an average value of the negative resistance balancing the loss mechanism. The Clapp oscillator is an architecture used frequently in RF applications. The schematic is shown here, and we can break it down into the functions like this. This L and this C3 are the resonator. C1 and C2 provide feedback from the output to the input. The transistor is the gain element. Typically there will be some DC bias connection. And the load is at the output of the transistor amplifier. Analyzing the circuit shows that the oscillation frequency is determined by a similar expression, 1 over 2 pi square root LC, where the C is a C equivalent combination of C1, C2, and C3. With voltage control of C3, we can achieve tuning of the oscillator. Here's a more detailed view of the Clapp oscillator. This is all DC bias for the base and the collector. Also DC bias for the emitter. The equivalent circuit is shown here at RF frequencies. And looking at the equivalent circuit seen by the resonator at the oscillation frequency, we get this expression for the equivalent impedance looking in. The negative resistance component comes from the term corresponding to the GM, the gain of the transistor. The GM function, which becomes limited at higher amplitudes, provides soft clipping. And again, the GM is the gain mechanism feeding energy back into the resonator. For startup, we do need to choose C1 and C2 for proper feedback to ensure that we have R neg greater than the worst case value of R loss. So to summarize the typical performance of oscillator architectures in this plot, frequency on the horizontal axis, better phase noise or spectral purity on the vertical axis. Multivibrator and feedback oscillators typically used at low frequencies provide poor to moderate phase noise performance. The ring oscillator can operate at very high frequencies and has reasonable phase noise performance, but for the best performance in both speed and phase noise, spectral purity, the resonant approach is the way to go. So let's look at some basic performance metrics for VCOs, frequency range and tuning range. We'll begin by looking at frequency, power output, tuning voltage, and the power supply. And we'll look at one example from the Mini Circuits catalog. The VCO is characterized by the frequency range it can cover, the tuning voltage required to exercise the VCO output over that frequency range, and the power supply required for the oscillator. Note that we may have the tuning voltage, V-tune, here which has a maximum of 18 volts, exceeding the supply voltage, which is only 12 volts. So in some cases, V-tune may actually be greater than the supply voltage. So if you want to exercise the VCO over its full range, you may need to take that into account in your system design. So basic performance metrics, again, the output power level in dBm. For a sine wave output, is typically specified in dBm provided into a 50 ohm load. For a square wave output VCO, the output level is specified in terms of compatible logic families. The DC supply required to power up the VCO. For the frequency range and tuning voltage range, again, we're looking at the functional variation of oscillator frequency versus tuning voltage. And we'll go between a min and a max. So looking at a plot for the JTOS 1000W oscillator, frequency as a function of tuning voltage shown over here at room temperature of 25 degrees C, roughly 440 megahertz to about 1070 megahertz. For the tuning range of 1 volt to 18 volts. Note that there is some temperature variation. For example, for this data point, 9 volts, we can see a small range from 775 to 750 megahertz. Depending on the application, that temperature sensitivity may or may not affect operation. In a phase lock loop, for example, the tuning voltage necessary to achieve a target frequency might change slightly, but very often a moderate temperature sensitivity, as shown here, is not a problem. Methods of tuning. We require electrical control of some parameter that determines frequency. For the multivibrator, it's typically the charge and discharge current. For the ring oscillator, it's that gate propagation delay. For the resonant oscillator, it's typically voltage control of capacitance in the LC. So for the multivibrator, frequency is controlled by current, capacitance, and the VREF thresholds. If a linear transconductance GM is used to develop the reference current from the tuning voltage, then we have a very linear characteristic relating the oscillator frequency to the tuning voltage. But it turns out that the multivibrator, being a first-order system, has an inherently poor Q, which, as we'll see, will lead to poor phase noise. And typically, multivibrators are limited to the megahertz range of frequencies. For tuning the LC resonator, a Varactor diode can be used to achieve voltage control of capacitance. Going back to some basic semiconductor device physics, the charge stored in the depletion region between the PNN regions of a diode is a nonlinear function of voltage. The capacitance, dQ/dV, is also, therefore, a nonlinear function of voltage. The nonlinear characteristic is characterized by three parameters: CJ0, the zero bias capacitance; the built-in voltage of the junction, VBI; and the grading coefficient, M, which is related to the doping profile of the junction. So, for example, in the Clapp oscillator, this was our expression for the oscillation frequency, rewritten in terms of the tuning capacitance, C-tune, which was C3. The tuning range is set by the range of capacitance values that can be achieved. The minimum and maximum voltage on V-tune will give us the minimum and maximum frequency range, and that's why typically we will go beyond the supply voltage. V-tune is only seen by the other end of the Varactor diode, so it's okay if V-tune exceeds the supply voltage. That will get us larger tuning range. Looking at some advanced performance metrics: tuning sensitivity, phase noise, supply pushing, and load pulling. Shown here, units of phase noise are dBc per hertz. Pulling and pushing are megahertz per volt, for example, for pushing. And tuning sensitivity, the slope of the characteristic, in megahertz per volt. So looking first at tuning sensitivity, tuning sensitivity is the slope of the plot relating the oscillator frequency to the tuning voltage. In this plot, tuning sensitivity scale is on the right axis, and we can see it varies from 65 megahertz per volt to about 30 megahertz per volt. So it varies by a factor of 2 over this frequency range. And we can see here's the variation from one end of the range to the other. In some applications, this is not an issue. In some, it is. One application where it is an issue is in the phase lock loop. The voltage-controlled oscillator in the phase lock loop, represented with the tuning sensitivity K0 parameter, the expression for the VCO loop bandwidth, or the VCO's impact on the phase lock loop bandwidth, omega L, it's directly proportional. So depending on the system, it may or may not be critical what the loop bandwidth is, but the value of K0 also does affect loop stability, which is certainly a critical consideration. So looking at the effect of the Varactor tuning characteristic on tuning linearity, the junction capacitance variation versus voltage is determined by the exponent m. The junction capacitance, in turn, affects the oscillator frequency. And we would like the oscillator frequency to be linearly related We want a linear relationship between the tuning voltage and the oscillator frequency. But for a step junction, the exponent m is roughly 1/2, meaning this exponent is only about 1/4. So with a very low value of exponent, it's not very sensitive, leading to a smaller tuning range, and it also means we have an inherently nonlinear characteristic. The hyperabrupt doping profile, shown on the right in this slide, gives an exponent roughly equal to 2 in the CJ junction capacitance characteristic, leading to an exponent closer to 1 for the oscillation frequency. The disadvantage of the hyperabrupt junction varactor, it turns out to have a slightly lower quality factor Q in the resonator, which gives worse phase noise performance. So looking now at phase noise, here's the picture from a spectrum analyzer at the oscillating frequency of a VCO. Ideally, a pure sine wave in the frequency domain is just an impulse at the oscillation frequency. Phase noise is manifested by looking close into the carrier. Here we're looking at a span of 1 megahertz on a 155 megahertz center frequency oscillating frequency. All of this power close in is phase noise. Why do we care? Well, in an RF system, if we're using a local oscillator to downconvert a channel from RF, the additional phase noise power on our local oscillator will convolve with the RF spectrum we're trying to downconvert and lead to a smearing out of the information in the frequency domain. It can also cause interference from an adjacent channel interferer if the interferer falls within the skirts of the phase noise of the VCO. In a digital system, phase noise is manifested as jitter, random variation in the zero crossing times of the clock at the VCO output. So this would decrease timing margin for any system using this clock. The shape of the phase noise spectrum comes from the transfer function of the LC resonance as seen by the white noise, the thermal noise, corresponding to the loss mechanism in the resonator. The transfer function shape filters the white noise into frequency regions close in to the resonance of the oscillator. If we can use a higher Q resonator, that pushes down the transfer function and improves phase noise. To get an intuitive view of phase noise, consider an ideal sine wave source shown on the left side of this slide with plots of the signal in both the time domain and the frequency domain. In the time domain, we've got a pure sine wave. In the frequency domain, an impulse. We'll then add wideband noise, shown in the frequency domain as a raising of the noise floor around our impulse, and in the time domain as fuzzy white noise being added to our sine wave. Now, to clean this up, we would use a narrowband filter because we need to keep this fundamental, and that will get rid of most of the noise, but close to the carrier, close to our oscillating frequency, the shape of the narrowband filter will give us close-in noise, both in terms of amplitude noise and phase noise. We can get rid of the amplitude noise by going through a hard limiter that eliminates the amplitude uncertainty, and that will decrease the noise power by a factor of 2. From our original noise, but the phase noise we can't get rid of, and that's what we're stuck with on our output clock. So describing phase noise, it's a power density relative to the carrier in terms of dBc. Since it's symmetric, we just look at a single-sided representation, and at different offset frequencies from the carrier, we'll just report the noise that we see. So going back to the spectrum we saw earlier, here's our 0 dB reference for the carrier. At an offset frequency of 1 kilohertz, we're 73 dB down, minus 73 dBc. At an offset frequency of 10 kilohertz, 94 dB down, and so on. So just looking at various offset frequencies, the further away we go, the lower that phase noise power density will be. Eventually we get to a roughly 20 dB per decade fall off. In phase noise power, and that comes from the shape of the spectrum. So sources of phase noise in the Clapp oscillator circuit. In our tuning signal path, there will be some noise sources there. The loss mechanisms in the tuning device are a source of phase noise, as well as loss mechanisms in the resonator and in the active device, our gain device, the transistor. Supply and load sensitivity, the output frequency can be affected by VCC and RL variations. The mechanism depends on the particular circuit architecture. Dependence on the power supply is called supply pushing. Changes in load behavior affecting oscillator frequency is referred to as load pulling. So the mechanism for supply pushing, if VCC changes, it'll affect the DC bias of the device, and any change in transistor bias conditions can affect internal signal amplitudes. Because this tuning characteristic is nonlinear, we will see some change in the effective capacitance and therefore the oscillation frequency caused by the change in power supply voltage. Load pulling, if the load is closely coupled to the output and is not matched, then parasitics internal to the oscillator, for example, the base collector capacitance, can feed back into the resonator, and reflected energy from load mismatches can couple back into the resonator and change the oscillation frequency as well. So, in conclusion, we've looked at some fundamentals of VCO operation. First, looking at first-order behavior, how the tuning voltage controls output frequency, and in the first-order behavior can be specified just by the minimum-maximum range of the oscillating frequency and the tuning voltage. Several performance limitations we've looked at: the linearity of the tuning characteristic, spectral purity of the output in terms of phase noise. We didn't look at harmonics, but similarly those can be analyzed in the frequency domain, and depending on the needs of the application, can drive selection of an appropriate VCO. And finally, supply and load dependence in terms of supply pushing and load pulling. We've taken a very brief look at different VCO architectures and how they trade among frequency range, tuning linearity, and phase noise performance. So at this point, we have some time left for questions, and I'll turn it back over to Pat to field some questions.
Great. Excellent presentation, John. Thank you very much. Yeah, we have quite a few questions here, so we'll get started. It said on slide 20 you mentioned that the performance is higher. Do you mean higher Q or higher performance?
For the resonant oscillator, let's see, slide 20. Yeah, higher Q and higher performance, they go hand in hand. And that's mostly for phase noise reasons. If we look at the, let me find that slide. Let's see. So phase noise, the phase noise power that we want to eliminate, get as close as we can to that ideal impulse. Any noise sources in the resonator will lead to this phase noise. So if we reduce the loss mechanism, we both reduce the source of the noise and improve the filtering to drive the transfer function closer to the ideal of an impulse. So a higher Q resonator will both give you better spectral quality and higher performance.
Great. Okay, which VCO architecture typically yields the best close-in phase noise?
The resonator would. If we look at the oscillator summary slide, the resonant oscillator will give you the best phase noise. The feedback multivibrator and ring oscillators, when you analyze them for phase noise or for jitter, the effective Q is typically equal to 1 because there's really only one energy storage mechanism. And there's also, for the feedback oscillator, for example, so much active circuitry you need around the RC network to ensure oscillation. In the resonant oscillator, you've got a lot of energy trading back and forth between the inductor and the capacitor, and it's really the ratio of the resonant energy to the random thermal energy that determines phase noise quality. And that the ratio of those energies is related to the Q of the oscillator. So if you're looking for a good phase noise performance close in, the resonant approach is the way to go.
Okay, next question. Is it always the case that the VCO will be frequency low at high temperature and frequency high at cold?
I would say no. Let's see if I can find... I would say it depends on the architecture and on what's causing the temperature variation. Typically, the bias conditions of the amplifier, for example, of the transistor, would be adjusted to partially cancel the effects of temperature variation. And if that compensation is overdone or underdone versus temperature, it might affect which way that variation in frequency would go. So I would say it's not something you would depend on for a basic physics reason. Usually you're looking at two circuit design considerations that are tending to cancel each other out.
Okay, what are the limiting factors in miniaturization for very low frequencies? Is it possible to make them, small scale for low frequency VCOs? For low frequencies, let's see.
for low frequencies, the resonant approach is going to have trouble since the resonant frequency is 1 over 2 pi square root LC. You can synthesize a lower frequency by operating a resonator at very high frequency and dividing down the output clock. But for low frequencies, the size of the inductor in particular can be very large. Now, I haven't talked about other resonances like crystals or saw oscillators. So there's other ways to achieve the resonance where the energy storage mode is a mechanical mode in a crystal. Haven't talked about those. Those, depending on the size of the crystal, you can get low megahertz type frequencies there as well. But for lower frequencies, sometimes you just run into the size of the resonator, and then you'd want to look at a multivibrator type oscillator, for example.
Next question, what advantages do coaxial resonator-based VCOs offer over standard LC-based VCOs?
I didn't really talk about the coaxial resonator. I suspect you'd be able to get much, much higher frequencies, and depending on how much energy is stored in the resonator, very high Q as well. I'll have to research that for the next version of this webinar.
Can you explain the specs for pushing and pulling, what they mean?
Right. So, let's see. Pushing and pulling. If we look at the specification, so the units for pushing and pulling. For pushing, it's in megahertz per volt. So 1 megahertz per volt says if I change the power supply by 1 volt, then I'm going to see a 1 megahertz change in my 1 megahertz change in my frequency. Pulling is typically specified in terms of reflection. So here, dBr. So in terms of reflected energy, for a certain change in reflected energy, you'll see this change in oscillator frequency in terms of megahertz.
Okay, what are the best ways of reducing phase noise?
Best ways of reducing phase noise. So in terms of oscillator design, using the highest quality resonator you can, once you've selected an oscillator for a particular phase noise performance, the challenge is really to don't screw it up. Don't in your system in terms of distributing the clock. Be careful that whatever you use to distribute a high quality low phase noise clock doesn't mess things up. For example, in the here on slide 56, the VCO output in this system is used in an I&Q type architecture. The distribution of the VCO through the mixer, you don't want to attenuate the clock if you can help it, because then any white noise in the signal chain beyond the VCO represents more phase. So it's really a matter of selecting a high quality, low phase noise signal source and then get that signal to where you need it without degrading its signal quality.
And kind of a related, how does a multi-loop oscillator provide better phase noise performance?
A multi-loop oscillator. I'm not familiar with the terminology multi-loop. I don't know if I'm not familiar with that terminology. I'll have to take that question offline.
Okay. Would a combination of high Q resonator and negative resistance amplifier give lower phase noise?
Let's see. So with the let me find the best slide to address that if I can. Here we go. So the the challenge is the loss mechanism has a thermal noise associated with its loss. I mean, that's just the way resistors with loss mechanisms are. The negative resistance that we add in, the function of that negative resistance is just to restore the energy lost in the resonator. It's important that, however we realize this negative resistance function, it be done in as low noise a fashion as possible. For example, in the Wien bridge oscillator, this amplifier is feeding in energy. We would want to use a low noise amplifier to make sure that the energy we're feeding back in also has low energy at the resonant frequency, since the noise of this amplifier will be included in whatever is present in the loop.
Can feedback design low noise VCOs such as 1 gigahertz and phase noise at negative 120 dBc per hertz?
Could you repeat that specification, please?
Frequency 1 gigahertz and phase noise negative 120 dBc per hertz at 10 kilohertz offset.
At 10 kilohertz offset. Let's see. I'm going to have to take that one offline because I do have some rules of thumb. If anyone wants to contact me by email, I can steer you to some resources where you can basically come up with some figures of merit for phase noise performance and see what's realizable as a function of oscillator frequency.
Okay, great. Can thermistors, so temperature control components in the bias circuit, control some of the temperature drift for VCOs?
Yeah, that's specific to the nature of the oscillator. So, for example, here on slide 65, it's shown in terms of supply pushing, but any change in the bias characteristics equivalent to what's caused by VCC is also going to cause a change in oscillator behavior. So thermistors, again, depending on the application, for a more integrated application, this bias might be provided by a current source, which could be controlled in temperature-sensitive fashion. Again, specific to the architecture of the oscillator, there are temperature compensation techniques available.
Okay, great. I think that about ends most of the questions. Anything we didn't get to, we can answer via email. John, thank you very much for a great presentation. Excellent job as usual. And I'd like to thank our sponsor, Mini Circuits. You can find out more about their products at minicircuits.com. Thank you for joining us today.
Thank you.